Okay, so let's start. In the last class, we saw three different bounds on the size of codes. So for a given minimum distance, we want to know what is the largest rate of a code that we can construct, or what is the size of the largest code that we can construct for a given minimum distance. Or another way to parameterize this is in terms of the number of errors that my code can correct. So we saw that asymptotically, for asymptotically large n, we've seen three upper and lower bounds. So two upper bounds were the singleton bound and the Hamming bound. So the singleton bound basically gave us this straight line joining 1 and half, so it is 1 minus 2p. The asymptotic Hamming bound is basically 1 minus h of p, and we got it by this sphere packing kind of argument. And then we also saw a lower bound, that is a way to construct a code in a greedy fashion, and that gave us the Gilbert-Verschamer bound, which is basically 1 minus the binary entropy of 2 times p. So clearly there's a gap, at least for asymptotically large n, there is a gap between the best upper bound and the best lower bound. And in fact, it is not even clear as to at what rate, at what value of p is r equal to 0, right? Because if you look at the GV bound, the rate is equal to 0 for any p greater than a quarter. On the other hand, the Hamming bound predicts that the rate is non-zero, or it's upper bounded by something which is non-zero all the way up to a half. So first we'll try to resolve what happens in this particular region. Is it possible to achieve a positive rate for any p greater than quarter, or in other words, any minimum distance greater than half? Okay, and then we'll try to derive a better upper bound than any of these, or at least for asymptotically large n. Now we've seen that for finite n, for certain configurations of n and d, you can't really say that one bound is strictly better than the other, because we saw some examples in the previous class where singleton bound actually beats the Hamming. But at least for binary codes and asymptotically large n, the Hamming bound is strictly better than the singleton bound, because it's always below the singleton bound. Right? Singleton bound is just a straight line, and the Hamming bound is this convex function 1 minus h2p, which lies below the singleton bound. So in today's class we'll explore two other bounds. In fact, briefly we'll try to see a third bound, but not in detail. But this bound will do better than both the Hamming bound and the singleton. So before we start, any questions? Okay, so the first question we'll try to answer is, at what rate or at what value of p is r asymptotically equal to 0? So for the rate to be strictly positive, you need at least an exponential number of code words, exponential in n number of code words. Is it possible to get a bound when the number of code words is not exponential, but maybe just polynomial in n? So polynomial number of code words would imply that the rate is asymptotically equal to, right? So these are the way we'll derive these bounds is using some combinatorial techniques. So we'll see a couple of functions. In fact, we will basically look at the minimum distance between all pairs of code words and try to manipulate this in a number of different ways. We'll first see what is called the Plotkin bound. And the way we obtain the Plotkin bound is the following. So suppose that I list all possible code words. Okay. 1, 2, all the way up to CM. It's an arbitrary NMD code. It's not necessarily linear, and let's say that I list down all possible code words in the form of a matrix. Okay, so this is an M by N matrix, M code words, N the block length. And let me look at the pairwise distance between every pair of code words. Okay, so I'll define S as summation overall X in the code book, summation overall Y in the code book of T of X. So I take all pairs of code words and I take the sum of the distances between the two. Okay, this is some quantity. So first, let us see. So what do I know about this particular code? I know that the minimum distance is at least D. Right? So for every pair X comma Y, where X is not equal to Y, I know that D of XY is at least D. So for any NM T, so I have X greater than D for all X not equal. So S, you can write this as summation overall X. And what is DH for X equal to Y? It is 0. The distance between every code word itself is equal to 0. Right? But this is greater than or equal to X C X. Right? So this summation runs over how many elements? The inner summation? M minus 1 elements. Okay. What about the outer summation? M elements. This is just M into M minus 1 into D. So this sum is lower bounded by M into M minus 1. So this is what I sort of call the row view of the distance. Okay, so I'm basically taking all pairs of rows, and then I'm sort of just looking at the distance between. So now I look at the column view for this particular code. We look at each individual coordinate and see what happens. So let me define this particular quantity. Which one? So I'm taking all possible Y. I'm not necessarily taking all pairs. So I'm running X over all code words, Y over all code words. So there'll be an XY and a YX. No problem. That's okay. Right now, this is the quantity that I am considering. Not necessarily distinct pairs. Just to keep things simple. Okay. So I'll define Ni comma alpha as, so for any I between 1 and n and alpha in the field. So Ni alpha is the number of times we see alpha in the ith column of that matrix. So in other words, I look at the ith coordinate of all the code words and I count how many code words in which the ith coordinate is equal to alpha. that is also equal to num code words C in the code book for which ith coordinate is equal to. I'll write it. I'll write this using indicator functions because it will help me later on. So can one of you suggest a way to write this in terms of indicator function? So suppose I look at the indicator function. X. Suppose that C of j. So C of j is the jth code word. Okay. So Cij is basically the ith element of the jth code word. So can you write this ni alpha in terms of the Cij's? Huh? Cij equal to alpha summation. Do you all agree? So I'm looking at, so basically I take one particular column, the ith column. So I look at the ith column and I look at the number of i's, look at the number of alphas in this. Okay. M of this. Okay. So now let me now what I want to do is basically write this in terms of these in terms of the ni alphas. Somehow I want to get. What do we have? S equal to nation overall y. So let's see what happens. Now let us look at each column. So I can also write this as summation I equal to 1 to m. Maybe say j equal to j1 equal to m. So j equal to 1 to m. So I'm going coordinate by coordinate. Sorry, let me go coordinate by coordinate. So summation I equal to 1 to n. In each coordinate, I'm trying to find out how many pairs are different. Right? So this Hamming distance is the same as summation overall a1 equal to m, summation a2 equal to m. So there's a contribution of 1 to the Hamming distance if whatever xi is not equal to yi. Right? Or if I look at the j1th code word and the j2th code word, then there's a contribution of 1 if ci of j1 is not equal to I of j2. So I'm looking at each, so I'm basically splitting this Hamming distance into coordinate by coordinate Hamming distance. Okay. n summation a1 equal to m, a2 equal to 1 m. So now I look at all those coordinates for which this is equal to, say, alpha. In field indicator, C1 this is equal to. So for the first code word, the whatever the ith coordinate is equal to alpha, and for the j2th code word, the ith coordinate is not equal to alpha. This is one way of writing it. Okay? So basically, there's a contribution of 1 to the Hamming distance in the ith coordinate if whatever the ith coordinate of the j1th code word is equal to alpha, and that j2 is not equal to alpha, and you take the summation over all possible. Seems like a complicated way of doing it, but I'll play some tricks here. So now let me interchange the order of summation. N to a2 equal a1 equal indicator I a1 equal to indicator I a2 is not equal to. Okay, so I'm focusing on the ith coordinate. What is this quantity equal to? That is basically ni alpha, right? So in this, I'm basically counting the number of code words for which the ith coordinate is equal to alpha. This is just our ni comma. Okay, that seems to have simplified things a little bit. Ci k2 not equal to alpha. This counts. So this, if I look at this particular quantity here, exactly. So it's counting the number of the number of code words for which the ith coordinate is not equal to alpha. Since there are a total of m code words, and out of which ni alpha code words have the ith coordinate equal to alpha, this is basically equal to m minus ni alpha. Basically, what we get is summation I equal to 1 to n summation overall alpha m minus ni alpha ni alpha. Let's try to quickly simplify this. So summation I equal to n alpha q m times ni alpha minus q ni n square I. Correct. Now I can take this m outside because it doesn't depend on the summation. Now what is this quantity equal to? Yeah, m. Right? You look at the ith coordinate, and so there are ni alpha code words for which the ith coordinate is equal to alpha. If I just sum over all possible values of alpha, then basically I'm summing over the total number of code words. What I should get is the total number of code. So this is just m times summation I equal to 1 to n of m. This is basically n times m. So this whole thing is just nm square minus summation I equal to alpha square. That's good. So we have some quantity over here. We know that S is exactly equal to this quantity. And we also have a lower bound on S in terms of m into m minus 1. Right? Okay. So now if I'm somehow able to get this quantity in terms of n, m, and d, I get a bound on I get a bound on m in terms of d, or d in terms of. Okay. So now how do I tackle this? So let me look at this particular expression. Summation alpha q n I. Right? I want to somehow bound this square. Now I know that m is equal to this, or m square is equal to this, the whole square. Correct? Which one? M square. So basically I want to bound on ni alpha square. Okay, or summation ni alpha square, summation overall alpha. Somehow I need to get. You agree that m is equal to summation overall alpha ni alpha? You're looking at the ith coordinate, right? Ni alpha is the number of code words for which the ith coordinate is equal to alpha. Since you're summing over all alpha, basically you're counting all the code words. So it's equal to the number of code words, right? So this quantity is equal to m. I'm just squaring both sides. Yeah. So right now what I want to do is I'm going to use Cauchy. So I can write this quantity as the inner product of the vector I, and I is equal to ni 0, 1 for all possible codes. It's a vector of size q, inner product with the all ones. You agree? Are you all with me? So this summation overall alpha ni alpha can be written as the inner product between the vector of ni alphas along with the all ones vector. That will just give me ni0 plus ni1 plus so on alpha. Okay. Now let me use the Cauchy-Schwarz inequality. What does it say? Correct. X transpose by the whole square is equal to the norm of ni square, the 2 norm, times the 2 norm of indicator. But what is the first quantity equal to? Is equal to summation I alpha in FQ of Ni square. That is the first term. What is the second term equal to? Is equal to Q. Okay. So what this basically says is that summation alpha in F2 Ni alpha square. So this is greater than or equal to M square divided by Q. Okay. So just quickly see what I did. I'm just writing S in two different ways. So for one, I had a very simple bound, M into M minus 1 into D. In the second case, I looked at it coordinate by coordinate. I showed that S is equal to Nm square minus summation over all I summation over all alpha of Ni alpha square. Now I basically want a lower bound on Ni alpha square. And that turns out to be, and just using the Cauchy-Schwarz inequality, I get that this is greater than or equal to M square by Q. So that S is greater than or equal to M into M minus 1 D, where it is also less than or equal to N M square. So basically I plug this in this particular equation, Nm square minus M square over Q. Yeah. So there's a summation N M square divided by Q, Nm square minus square divided. So this is in other words is the Nm square into 1 minus Q. On the left hand side, I have M into M minus 1 into D. So I can cancel out one of these M's. Get M minus 1 D is less than or equal to Nm into 1 minus inverse 1 by Q. Now I want to bound on M. So let me take all the M terms on one side. So M into D minus N into 1 minus Q inverse less than or equal to D. So I take this D term to the right hand side. I bring all the other terms to the left hand side. I basically get this. So M is less than or equal to D divided by D minus N into 1 minus Q inverse. Now I have to be careful over here. This makes sense only if D is strictly larger than N into 1 minus Q inverse. Right? Otherwise, this right hand side is negative, so it gives me something. And I know that M has to be an integer, so because M is the number of code words, so M is less than or equal to the ceil of D divided by D minus N into 1 minus Q inverse. For D greater than So this is called the Plotkin bound. Right? So we're getting a bound on M, which is now not exponential in N. Right? So D can be at most N. So the largest the right hand side can be is N divided by N minus N into 1 minus. It is something which is at most linear in N. Right? So this means that the rate is asymptotically 0 for all D greater than N into 1 minus Q. If we want to target a D which is larger than N into 1 minus Q inverse, then the rate tends to 0 and tends. Okay. And what happens in the binary case? If D is greater than Q inverse is half, so 1 minus half is half. D greater than N by 2 R tends to 0. Or in other words, P greater than 1/4 R tends to 0, N tends to infinity. So now if I go back, this basically the Plotkin bound the Plotkin bound says that the rate is equal to 0 in this entire. This is for binary codes, asymptotically large. But in general, this is a very tight bound. So basically for large minimum distances, this says that it is impossible to get positive bit. So for large distances, this gives a very tight. Just quickly to recap what we did, we basically wrote the sum of the distances between pairs of code words in two different ways. One explicitly as it is in terms of the distance between x and y for all pairs x and y. We saw that that is greater than or equal to m into m minus 1 t. And then we looked at it from the column perspective. So for each coordinate, we counted the number of pairs of code words for which the ith coordinate is different. And we showed that that is equal to nm square minus this particular quadratic term. And to bound this quadratic term, we just basically use the Cauchy-Schwarz inequality. Showed that this quadratic term is greater than or equal to m square by q, and then substituted it back to the expression. So we got that the number of code words can be at most d divided by d minus n into 1 minus. So since d can be at most n, log m divided by n is something vanishing in n. So the rate is vanishing in n as long as d is greater than n into 1 minus 1 by. Any questions? Okay, so that kind of resolves the picture for p greater than 1/4. But then there's still this big region over here. So we know that for any point to the right of 1/4, we cannot achieve a positive rate. But now there is this big gap between the Hamming bound and the GV bound. Can we improve upon this? So essentially, what we need is a bound which kind of tends to which kind of tends to 0 as p tends to 1/4. So firstly, is there such a gap, or is there some kind of a sharp trans what we want to resolve? So these ideas can be used to, or similar ideas can be used to get a better bound in for p between 0 and a quarter. This is what is called the Elias bound. Okay. And it's kind of complicated looking bound. So since we'll have this 1 minus 1 by q appearing multiple times, I'll set some notation for that. So let us define r to be equal to 1 minus by q. Take any w which is less than or equal to r times n. Some parameter for now, w is going to be less than or equal to r times n, and w square plus nr w plus nrd greater than 0. I'm going to pick a w which satisfies these two constraints. Any number w which is less than or equal to r times n, 1 minus 1 by q times n, and w square plus 2nrw plus nrd is greater than 0. Suppose I pick something of this. Pick a w which satisfies this. Then capital M is less than or equal to nrd divided by w square plus 2nrw nrd q to the n divided by pq. Remember that this is the volume of the Hamming ball of radius w. Remember, for each w which satisfies these constraints, I get a bound. Right? All of these are upper bounds. So the minimum over all possible w which satisfies these constraints, or the minimum on the right hand side with respect to all possible w satisfying those two constraints, gives me the best possible bound. So M is in fact less than or equal to the minimum over all possible w which satisfies constraint 1, constraint 2 of this particular. Now it's difficult to probably visualize what this looks like, but it's still possible to numerically evaluate it, right? So in fact, if you look at asymptotically large n, then and q equal to 2, so if we take f2 and n tending to infinity, then we get that m is less than or equal to nr d divided by 2r w plus nrd. Now all of these are basically polynomials in n, right? So they don't really affect anything as long as this will be the dominating term. This will be 2 to the n divided by vq of nw, which grows as 2 raised to the binary entropy, n times the binary entropy. This will be 2 times n into h2 of w plus whatever this bit low. So this is basically equal to 1 to, so the asymptotic rate is equal to 1 minus h2 of w for any w which satisfies these two constraints. So that gives us an expression we can evaluate. It may be good, it may not be good. We can't really say just by looking at this, but it gives us a bound. So in general, the Elias bound is weak for finite n. But as it turns out, if you try to plot the Elias bound over here for the binary case and asymptotically large n, then we get something which looks like this. So this B all previously known bounds. Okay? But there's still a gap. Doesn't give us not equal to the GV bound. So how do we prove such a result? Right? And where did this W come from appear magically? Right? So for this we'll need some sub results. Okay. Okay, so I have some particular W, and what does that W correspond to? It turns out to be the weight of the maximum weight of a particular code book. So now instead of looking at all possible code books, let me see what happens when the code book is restricted to have a certain Hamming weight. Instead of imposing a maximum Hamming weight on the, a minimum Hamming weight on the code, I'll say that I want to look at all possible code books for which the maximum Hamming weight is at most W. So suppose I have any NKD code in capital K D code. So it has capital K number of code words. And all code words Hamming weight less than or equal to W, which as we saw is less than or equal to R times N. Then we can get the following bound. P is less than or equal to A times W divided by minus 1 N, or stated differently, less than or equal to NRD divided by plus NR. Plus NR. Okay, so this is something similar to what we saw in the Plotkin rule, right? So the size of the code book is less than or equal to some quantity, but this grows only polynomially. But now what is the difference? The difference now is that I'm restricting the maximum weight of the code book. I'm looking at all possible code books for which the weight is at most W. So the geometric intuition is the following. So what did we do in the Plotkin to derive the Plotkin bound? We basically showed that if the code book has, if you want the minimum distance to be sufficiently large, then the code book size cannot be any larger than whatever polynomial in it. right? Or put in a slightly different way, if you want to choose any more than a certain polynomial number of code words, then the minimum distance can't be any larger than whatever d over 2. Oh, sorry, n over 2 for the binary case. So the geometric interpretation behind the Elias bound is that now you look at this code, right? So we derive a weight constrained version of the Plotkin bound. This is basically a weight constrained version. You look at any ball of radius w, right? And look at the subcode book corresponding to all code words within w. So I have a big code, right? I zoom in within one particular ball at any point, right? So this forms a subcode. For this subcode, I'll try to derive a weight constrained version of the Plotkin bound. Right? So that will tell me that if the number of code words is more than a certain amount, then the minimum distance can't be any larger than. This is basically what this is saying. This quantity, the minimum distance is bounded by this. So this is for one subcode. So this has to happen no matter where I zoom in, right? As long as W is fixed, the radius of the ball is fixed, I'll zoom in over here, I get the same bound. So I can't have more than a certain number of code words in this region over here, can't have more than a certain number of code words in this region over here, and so on. So the Plotkin, the original problem with the Plotkin bound was that I get whatever a polynomial bound in terms of the number of code. Right? I want to somehow translate this into an exponential bound in the number of code. So positive rate implies that the code book should be of exponential size. Yeah. Correct. So minimum, not minimum Hamming weight, minimum Hamming distance. Correct. Correct. The maximum Hamming weight of all. Correct. Code book. Correct. Yeah, I want an exponential bound on the size of the big code, of the overall code. So what I'm doing is I'm viewing the big code book, actual code book, as a union of various subcode books. Right? So that is basically, I look at all of these balls, right? I look at all the code book within each of these balls. Correct? So what do I get? I get that the number of code words within this ball can't be more than a certain number. Same thing happens within this ball, and so on. So within each ball, I can't have more than a polynomial number of code words, but the number of balls is exponential in n. So overall, I'll get an exponential bound in terms of the code. Okay, that's the sort of the high level picture, and that's exactly what is happening over here, right? So this is the ball of radius w, correct? So I'm saying that within each ball, I can't have these many code words, but the number of balls is q to the n divided by the volume of each ball. So overall, the number of code words can't be any more. Okay. So now this essentially for this I need a weight constrained version of the Plotkin board, which is exactly what I have over here. K is less than or equal to nrd and divided by w square minus 2 nrw plus nr. Right? Okay. So the idea is pretty similar to the Plotkin bound. So once again, I'll define ni comma alpha as the number of code words c for which ci is equal to but now I need to somehow adapt this the case where I have a Hamming weight. So what do I know? Once again I have summation I equal to alpha n I comma. So what is this equal to? It's equal to k, right? The total number of code words. Now, since I have this additional weight constraint, I look at another quantity. So I look at summation over all n I. So I have this big matrix, right? The code book matrix. It is an m by n matrix where the jth row basically gives me the jth code word and the ith column gives me the ith coordinate. And so summation I equal to 1 to n I 0 is basically the number of zeros I have in this entire matrix. This number of zeros per matrix. Sorry? Correct. So now I'm the code book is of size capital K. I'm choosing this K instead of M because M is the size of my original code, whereas K is going to be the size of the subcode. I know. So if you want some other notation, let me know. M1. Huh? M1 is better. Okay. M prime. Okay. M1. Okay. This is fine. Which one? So it's the subcode. So right now everything is with respect to the subcode. If you forget about the other code. So this is the subcode. The subcode is such that the Hamming weight is less than or equal to W. All code words is less than or equal to W. Now I want a bound on this quantity T. This is the total number of zeros I see in the code word matrix. Right? So now this is basically you sum over all possible code words and all possible coordinates. Right? So in each code word, how many zeros would I expect to see? Number of zeros. What can you say? There's a weight constraint, right? Number of non-zero elements is less than or equal to. So the number of zeros should be greater than. Correct. So this should be greater than n minus w. The number of non-zero elements is less than or equal to w in each code word. Therefore, the number of zero elements should be at least n, should be greater than n minus. So, so what can you say about T? So this is true for each code word. And how many code words are there? M1 code words. This is M1 times N minus W. So that is one bound on T. Now similarly, I look at the following quantity. So remember that earlier we applied Cauchy-Schwarz inequality on the n vector, the ni vector. Now what I will want to do is I want to sort of differentiate between zero elements and non-zero elements, right? Because of this weight constraint. So I want to look at all the non-zero elements in FQ. Are basically the non-zero elements of FQ. Okay, so I want to bound on this. So now my new ni vector, let me call it ni prime. Whatever L, let's call it ni bar or tilde vector of alphas or alpha not equal to. What is the length of this vector? Sorry. Remember, it's a for each field element I have a number, right? So originally ni was a q length vector, right? So now what will it be? Q minus 1. I'm just looking at the non-zero elements. The number of times that particular non-zero element appears in the ith coordinate. Number of code words, so ni alpha is the number of code words for which the ith coordinate is equal to alpha. And I'm fixing one particular coordinate beforehand. And in that coordinate, I'm looking at how many times 1 appears, how many times 2 appears, how many times 3 appears, and so on. I don't care about how many times 0 appears for now. So this times inner product of the all ones vector of length q minus 1 with itself is what? It is greater than or equal to star the whole square. Again, just Cauchy-Schwarz inequality. Right? So this is q minus 1. This is whatever, it's some quantity that I'm in alpha in q ni alpha square. So this is q minus 1. Let me take it to the other side. So I get 1 by q minus 1. But what is this equal to? Yeah. M1 minus. It is not M1 square, right? I'm summing only over the non-zero elements. Not summing over all the i's yet. So it is basically M1 minus ni0, ni0, the whole square. But summation overall I ni0 was basically equal to t. Summation overall 0 square. So I'm going to apply Cauchy-Schwarz once again. So if I sort of expand this out, I'm going to get a term in terms of m1. I'm going to get a term in terms of summation ni0, but then also have a summation ni0 square. So basically the game is to somehow eliminate all of these ni alpha squares. Right? So you write whatever the sum of the minimum distances in one way, right, in terms of t or m1 or whatever, and then in another way in terms of the ni alphas, and then you try to get rid of the ni alphas in some. Okay, so we can get rid of all the other ni alphas, but now we still have an ni0. Okay, for which I'll use the Cauchy-Schwarz again, but in a different way. So now I look at the n length vector of ni. N1, 0, N2. So the inner product of this with the all ones vector of length n is going to give me summation overall I ni0. So this times the inner product all ones vector n. This is greater than or equal to summation 0 the whole square, or summation I equal to n a 0 square greater than or equal to 1 over n. What is this quantity equal to? Defined it over here as t. 1 over n time. Okay. Now let's go back to the quantity that we have, right? So we had t greater than or equal to m1 into n minus w, right? That's one thing we had. And now I have another bound on summation overall alpha in fq ni square. So let's maybe list out everything that we have. So this is equation number 2. Fq star ni alpha square. This is greater than or equal to 1 over q minus 1 into m1 minus a0 whole square. And what else did I have earlier? Yeah, so t is greater than or equal to m1 into n minus w. n minus 2. So now I can substitute, I can kind of, wherever I have m1, I can, sorry, wherever I have t, I can somehow try to substitute m1 into n minus w, so that will get rid of t eventually. But now I need to connect m1 and the minimum distance. So the minimum distance is not appearing anywhere over here. Right? So let me look at the s term once again. So s, this is summation over x. Good. So I'm looking at the same term that I was looking at earlier. I know that this is greater than or equal to m into, sorry, m1 into m1 minus 1 as earlier. But this is also equal to summation overall I equal to 1 to n summation over alpha equal to n times m square minus in fq ni. Right? So this is what I had earlier. Again, just from the Plotkin bond. I just apply plain, what are the first few steps of the Plotkin bond. I get this for this code. Now, the key difference between the original Plotkin bond proof and this is to split this in terms of the zero elements and the non-zero elements. So I have m1 into m1 minus d to be less than or equal to nm1 square minus summation I equal to 1 to n of ni0 square minus summation I n summation of ni alpha. Okay? And I'm going to use different bounds for each of these, the main trick. So I have a bound for ni0 square, which is 1 over n t square, which is again is greater than or equal to 1 over n into m1 square into n minus w the whole, less than or equal to n m1 square minus m1 square into n minus w divided by n minus summation I equal to 1 n. Now I use the other bound for this, ni alpha square summation overall alpha. So I use this particular 1 over q minus 1 q minus 1 into m1 minus ni0 the whole square. m1 1 square into minus by q minus 1 into one square plus 0 square so again I'll have to use some more bounds. I mean the same bounds. square into q minus 1 summation overall n I equal to 1 to n of m1 square. That will just give me n times m1 square. So summation overall I n I0 square I had found. So this is greater than or equal to 1 over n m1 square into n square. Minus, so summation I equal to 1 to n 2 ni0 m1. So summation I equal to 1 to n ni0, that's just t. So this is 2t m1. But now again I have a bound for t as m1 into n. It's a long complicated expression. And whatever. So basically we just so on the left hand side I have m1 into m1 minus d. On the right hand side I have this big complicated expression. So just maybe to save time, and it's not terribly insightful, it is just routine simplification. So you'll get m1 into m1 minus d is less than or equal to m1 square w 2 minus q divided by Rn. Looks much simpler. So m1 into m1 minus d is less than or equal to 1 square w 2 minus q by Rn. So much simpler than this. You can now cancel out one of the ones and you get d is less than or equal to m1 by 1 minus 1 q divided. So once again I get a plot. If I want to write it in terms of 1 less than rd divided by w. W square plus to get a polynomial upper bound number of words for any codebook which has a maximum weight constraint, as long as this constraint is satisfied and w should be less than. So that's sort of one step of the proof. So right now I've shown that if the code is weight constrained, then I have this particular. Now I want to show that this can be used to get a bound on the original code. I gave some intuition saying that basically you zoom into each part and therefore you can and you take all the sum of all these parts and you get this overall. But that needs to be formally shown. And for this I need the following level. So take any NMD code. Okay, remember, all I'm interested in is the parameters, right? So if I'm given any NMD code, it's possible to construct some code exists in KD code, same minimum distance, but now codebook has a different size with maximum weight W and A greater than 2 M times Q of NW. So given any NMD code, you can construct an NKD code. It doesn't, I'm not saying that this is exactly a subcode of the original. It turns out that it's going to be a subcode, or it's going to be obtained by taking a subcode and shifting it so that the center is equal to 0. Right? So what does it say? So I have this code, right? And in some sense, I'm trying to take the largest subcode, which has maximum weight W and minimum distance B, right? So what can happen is, in the original code, maybe this is the 0 vector. Possible that there are many code words on one side, but it's basically sparse everywhere else. So then what we do is, you take this particular subcode and then shift it so that the center becomes equal to 0. That will give you one particular subcode. So essentially what I do is, I take the code, I take the largest subcode which lies within a ball of radius anywhere, irrespective of where the center, because then I can recenter it. So this is equal to the maximum overall possible centers of the size of, so I take the ball of centered maybe at 0, radius W. So this is the ball ball of radius W intersected with what, I can shift the ball or shift the code. So this is my K, this is going to be my K. I want a lower bound on K in terms of M, or maybe I should have. This is greater than or equal to the average of this particular quantity when averaged over all possible x. I'm taking the maximum, I'm taking the x for which some shift gives me the code book, the sub code book of largest size. And now I just take the average over all possible shifts. The maximum anyway has to be greater than or equal to the average. So it is, there are a total of 1 over q to the n possible shifts, q to the n possible values of x times summation for all possible fq to the n 0w this is n q to the n. But what is this equal to? You can write this as q codebook So I'm counting a 1 if c plus x equal to an element from the shifted version of the code. This is an element from the ball. And basically now the trick is to just interchange the sum. So for a given b and c, there exists exactly one x for which b is equal to c. b q b in c of summation over all x of this later b is equal to x. Since it is a field or what it's a vector space, there is exactly one x for which b is equal to c. X is equal to b minus. So this entire quantity basically equal to, I'm taking one of this summing over all c, summing over all b. M1 is greater than or equal to 1 over q to the n times the volume of the ball is vq of n comma w times the size of the code book is m. That's basically, that's exactly what we have. So for any code book, I can construct a sub code book of size at least. But now this sub code book has weight, all code words of weight at most w, for which I have an upper bound on size of the subcode. From M1, M1 is upper bounded by NRD divided by square NRD, but then this is less than or equal to the q of NW divided by q to the m. So therefore m is upper bounded by q to the n by vq times this particular, which is gives us the Elias. So again, the proof is complicated because it involves a bunch of different tricks and a lot of the kind of simplifications and playing around with algebra. But the most important thing is to get the intuition. You can't be expected to remember the proof. The main idea was that there was this Plotkin bound which holds for an arbitrary code, but it gives you whatever, a linear upper bound on the size of the code book. The idea here is to take this weight constrained version and then look at the weight constrained version. So translate a linear upper bound into an exponential upper bound. And that basically gives us this curve. So the blue curve over. This is weak in general, but for certain special cases, it is good. At least better than some of the other two. Any questions? Okay. So maybe I'll spend 5 minutes and then we can stop. So it turns out that the Elias bound is not the tightest bound that is known. You can derive much tighter bounds, but then you can't, in general, you can't obtain closed form expression using those techniques. So you can formulate this problem of finding the size of the largest code book as a linear program and then try to solve that linear program numerically. That gives us what is called the class of linear programming bounds. And the idea behind the linear programming of the LP bounds is, instead of looking at just the size of the code book, you look at the distance distribution of the code, right? Or sometimes the weight distribution of the code. So you define BW for 0 n. So BW is going to be basically 1 over the size of the code book summation overall of the number of code words which are at a distance w to x. Okay. So what do we know about BW? Since the minimum distance is d, BW should be equal to 0 for w between 1 and d minus 1. Because there are no pairs of code words which are at a distance 1, distance 2, distance 3, distance d minus 1. What can you say about B0? So to every code word, how many code words, what is the fraction of code words which lie at distance 0 to it itself, right? So basically this quantity is 1. So B0 is equal to 1. So these are two constraints on these numbers, BW. So we have these two constraints. And what can you say about summation over all W 0 to n? Yeah. I know, but can you think about what that will be equal to? So basically, I'm taking summation over all W, right? So I take that summation inside. So summation over all W of the number of code words at distance W to X. What does that give me? What n is the block length, right? Size of C times summation X C summation over all W of good word to X equal to size of length of x is n, yes. So remember, this is the total number of code words at distance 0 plus total number of code words at distance 1. So take any particular code word, right? We're counting the number of code words at distance 0 is itself, plus the number of code words at distance 1, plus the number of code words at distance 2, plus number of code words at distance 3, and so on. So that will be equal to the size of the code book itself, right? So it is just the size of the, so this is basically equal to the size of the code book, then this summation divided by size of C. So this will just give you the size of C. So the size of the code book is now a linear function of the BWs. And I have some constraints. BW equal to 0 and B0 equal to. Now, this, in fact, it turns out that this is not enough. We need some more constraints because I'm not really imposing any structure of the code on this yet, right? So I have a linear, kind of a linear program, but that's not enough. So the main trick, again, I will not go through the details, but one key trick is to define the following polynomial. So K, L, N, Q, X. So this is defined as summation A equal to 0 to L. So it's a degree L polynomial. It's a complex Q minus 1 raised to L minus A X choose J. So basically x choose J is x into x minus 1, x minus 2 up to x minus J divided by J factorial. Similarly, n minus x into n minus x minus 1 and so on divided by k minus J factorial. So this will be a polynomial in x, correct? Right, but the coefficients can be complex. So this is called maybe it's a bit complicated. Sorry. Yeah, no. J is the index, right? So it is minus 1 raised to. Sorry, my bad. So J is going from 0, so it's a real polynomial. But in general, it can be negative. It's not necessarily positive. But it turns out, so the key thing to show is that summation W equal to 0 to N dW Q of W. So this quantity is always non-negative. 0 less than L. So if the BWs actually correspond to the distance distribution of a valid code, then this set of inequalities must. So now I get another set of n plus 1 linear inequality. And now I can try to solve this linear program of maximizing summation BW subject to this constraint, and these constraints. And that gives us the best known upper bound on arbitrary codes, which looks It's in between the Elias bound and the GV bound. But now there is still a little bit of a gap between the LP bound and GV bound. So that is really the best known results on the size of binary codes for asymptotically large. So in general, for any n and d, the LP bound generally gives you the best possible upper bound. It's not a closed form expression. You have to solve some linear program. And that involves a fair bit of complexity, but 2 minutes. But then it can be solved. You can get a numerical answer. But for q equal to 2 and asymptotically large n, it turns out you can get a closed form expression for the LP bound. It's a rather complicated expression, and you can plot it. It will beat the Elias bound, but it still does not meet the GV bound. Any questions? Okay, so then let's stop here. So this kind of concludes our discussion on combinatorial techniques in coding theory, deriving bounds on the size of code. So from the next class onwards, we'll try to see how to construct codes, right, and how do you decode them. In particular, so far we had a combinatorial treatment of coding theory. From the next class onwards, we'll see an algebraic view of coding theory. So some of the classical codes were constructed using algebraic techniques. So we'll first explore the structure of finite fields. How do you construct a finite field? What is the algebraic structure of any general finite field? And then we'll see two classes of codes, Reed-Solomon and Reed-Muller codes, and see how do you encode them, how do you decode them efficiently. And after that, we'll get into sort of the graphical view of coding theory. How do you construct codes from graphs?